In this video, we discuss learning outcome number 6 from lesson 5.1, which is all about applying our understanding of expected value to make decisions. Most of the applications here involve gambling. So let's revisit this idea of expected value. The expected value E of a discrete random variable X is the theoretical mean value of infinitely many trials. So you calculate the expected value in the same way that you calculate the mean, which is this. You take the random variable, you multiply by the corresponding probability, and then you add all of those together. That's the mean. Now the way we interpret this is that this is the average value that we would expect if the procedure were repeated indefinitely. So let's say you're making a bet and we're finding the expected value of that bet. So that's the amount that you would tend to lose or win, and then averaged if you continued to make this bet over and over again, repeated indefinitely. So if you were able to make infinitely many bets and then you were to calculate the average amount that you won or that you lost after infinitely many bets, what you would end up with is that expected value. Now, the expected value doesn't tell you anything about what's going to happen in the next bet. It just tells you what the average would be if you were to bet indefinitely. Another way that you can put this is that, you can't actually repeat that procedure indefinitely, but if you repeated that procedure often, a lot, many times, so the number of trials was very, very large. If that were the case, and then you were to calculate the average value that you lost, how much you lost or won per game or per bet as you continue to gamble in this way, that average value for that sample is going to get closer and closer to this average value that we would expect to get if we were repeating that procedure indefinitely. So you can think of this as being the average amount that you would win or lose if you were playing for a really long time. And this is like in a limiting sense, if you were playing indefinitely, if you were playing forever. This can help us to make sound decisions. Now let's say you've got $5 to place on a bet at a particular casino in Las Vegas, and you've narrowed your choices down to one of two bets. You're either going to play roulette and bet on the number 7. It'll cost you $5 to play, but if you happen to win, you'll win $180. Or you're going to play craps. Here you're going to bet on the pass line. Assume that you double your money if you win. So it costs $5 to play. If you win $10. Now it might seem on the surface that roulette is the better way to go, but it really matters what the probability of winning is and what the probability of losing is in both cases. Both of those are going to affect the expected value of playing roulette or playing craps. So let's review a little bit the rules of the game. I actually didn't know the rules of roulette until I started teaching this class. Here are the rules. The roulette wheel actually has 38 slots. One slot is the 0 slot, the other slot is another slot is the 0 slot, and the rest are numbered 1 through 36. If you win, so if the little ball, I believe it is, lands on the 7 slot right here, well, then you're going to win $180. If the little ball ends up anywhere else, you lose your $5 bet. So that's one game, one option. Our second option is to play craps. And the most common bet in craps is to bet on the pass line. Now, listing all the probabilities for craps is relatively complicated, or I understand it's relatively complicated. I watched a video on the Caesars Palace website trying to learn how to play craps. They mentioned a couple of ways that you could win and a few ways that you could lose, but they did not talk about a number of other ways. So it wasn't clear what the probabilities were. So instead of teaching everyone how to play craps and teaching myself how to play craps, I've just listed the probability of winning and the probability of losing right here. The probability of losing is 251 out of 495 when you're betting on the pass line. And the probability of doubling your bet is 244 out of 495. So The probability of winning is slightly less than the probability of losing. Now, if you're trying to decide between the options, one way that you can decide is to think about the expected value for each bet. Now, there are pros and cons to this, because remember that expected value is the expected value, or the expected average, loss or gain if you were to repeat this bet over and over and over again. This really doesn't tell you anything about one particular bet. But let's say you're playing roulette and you want to calculate the expected value. This is a good opportunity for us to practice calculating expected value, so we will. And we're betting $5 on the number 7. Recall that there are 38 slots in the roulette wheel. In order to calculate the expected value, we're going to fill out this table over here. The random variable x will be the amount that we lost or the amount that we gained when we played roulette. And then the p of x over here is the probability of winning or the probability of losing. So if you lose and you made a $5 bet, you lost $5. Now, if there's only one way to win out of 38 slots, there are 37 ways to lose. So you have a probability of losing of 37 in 38. Now, when you win $180, but you paid $5 to play. So the net gain to you is $175. There's a 1 in 38 chance that you'll win that $175. Now, if we want to find the expected value, we take these x values over here and we multiply by the probabilities over there and we add them together, and that's expected value. Now we want to compute our loss and our winnings and the probability of each, like we just did on the last slide. Then we want to compute the products, and then we want to add them to get the expected value. So you've got -5 times this fraction plus 175 times this fraction. If you add them together, you get this -0.26 approximately. So what this is telling you is that if you were to repeatedly bet on that 7, and you bet on that 7, and you bet on that 7, and you were to do this infinitely many times, then you could expect to lose 26 cents for every time that you played. Or you could say, after a really long time, after lots of different bets, maybe 1,000 bets, the average that you make or lose by playing is about 26 cents per game. So it's definitely stacked in the house's favor. You are going to tend to lose, but you're not going to tend to lose much per game. You're just losing 26 cents per game. Now, if that's what happens if you play a lot of games, so that 26 cents per game can add up if you're playing a lot of games. So that's our expected value for playing roulette. Now with the craps option, the probabilities were given to us. The probability of losing was 251 out of 495, and the probability of doubling the bet was 244 out of 495. So when we fill in our table over here, if we lose $5, and the probability is the 251 out of 495. If we win $10, but we spent $5 to play, so we have a net gain of $5. And the probability of having that net gain of $5 is 244 out of 495. If I want the expected value now, I multiply in each row and then I add the results. If I take this number and I add this number, I get about -7 cents. So this is telling me that if I were to continue to play craps and continue betting on that pass line, after a really long time, I would lose about 7 cents per game. So if I'm not too worried about, if I am not too worried about losing, if I'm worried about losing, then I probably shouldn't play, because the expected value either way is negative. You're going to lose money as you play for a really long time. If you play craps and you're betting on that pass line for a really long time, you're going to tend to lose about 7 cents every time you bet. And if you're playing, betting on a single number on that roulette wheel, you're going to lose 26 cents every time. So now you have to ask yourself, Would I rather lose 26 cents every time I play or 7 cents every time I play? And I think everybody would rather lose 7 cents because you're comparing that negative 7 cents and that negative 26 cents to each other. Now you might think, oh, I'd rather play roulette because if I bet $5, I could win $180. Now with craps, the amount that you win is exactly the same amount as you bet, at least in the version that we are playing here. So that $5 bet becomes $5 more. And you might think that because you would win $180 playing roulette, that might be the way to go. But if you look at this over a really long time, as you bet repeatedly while you play roulette, or you bet repeatedly while you play craps, you tend to lose 26 cents per game when you play roulette. And you tend to lose 7 cents per game when you play craps. So I think I'd rather lose 7 cents than 26 cents. So craps is the way to go, even though it might not be intuitively what you thought would be the better bet. So this is an application of expected value in decision theory. Now, again, remember how we interpret this. This is only after a really long time, after lots of bets. This really doesn't tell you what's the better choice when you're deciding between one bet over here and one bet over here. But I guess it's better than nothing. And you could say, well, maybe I'd rather lose 7 cents than 26 cents, so I'm going to go with craps anyway.